My name is Preston Holmes. I'm a solution architect on Google Cloud Platform, and I work on projects with connected devices, otherwise known as the Internet of Things, or IoT. And I want to start with answering definitively a question that often comes up, and that is, do we have a consensus as to what is IoT? And definitively, I'll say, no, we do not have any consensus about what exactly IoT means. And so I'm going to give you my working definition that I find useful for this, and that is that IoT is really a period of transition and transformation, and that we have everyday objects, things in our lives, and they serve some primary function. And that at some point, we begin to connect a few of these in this sort of awkward phase where some of them are connected to the network and many aren't. And this is really IoT, this sort of awkward transition. And then eventually, as all of these devices become connected by default, they're no longer really IoT. They just become the things that we have in our everyday lives. And so it's this transition and more of these things in our lives becoming connected by default that defines what is IoT devices. Now, if that's one working definition of what is IoT, then why are we wanting to connect all these devices? What's the point of it all? And it's really about getting access to information that wasn't previously available. So there's information in the environment all the time, all around us, but it's not really available to us as data. So this information might be something like the speed of a delivery vehicle, the utilization of parking in a city setting, might be more information about the yield and defect rate of manufactured products. No matter which vertical or industry you're in, there's probably information that's valuable to you that you're not getting any access to today. And so this is one goal for the Internet of Things, to go from information to insight. Now, most of the data that we deal with today in a big data context is born as digital data. Clicks on a website, application downloads, online commerce transactions, all are born as digital information. But the kind of information we're interested in the Internet of Things is analog, and we need a way to capture that analog information and then locate it to the places where we can work on it with the big data tools. So really, the Internet of Things becomes the set of technologies that are the means to this end. And this is really what I mean here when I talk about an end-to-end solution around IoT. Now, you've likely been hearing about the Internet of Things for some time, and the question comes up, why hasn't it been more fully realized? And there's a number of reasons why people have been held back, but first and foremost, I think, is really the complexity of the domain that's involved. You've got to determine and choose some sort of hardware device platform. You've got to pick whether or not to run an operating system and which operating system to run. The networking in the Internet of Things is a lot more varied and diverse. Some of these networks are much more spotty, much more expensive. There's whole new classes of networks being built specifically for IoT applications. You have mobile and cloud application development, each of which are their own sort of complex domains. And all of these devices have the potential to generate a lot of data at scale that might challenge traditional data infrastructure. And then finally, we all recognize that this has to be done securely. All eyes are on the security of IoT. And the good news is by paying attention to it early, we have the chance to design security in upfront rather than act reactively, which is a lot of what happened with the web. So the technology, and to solve this sort of end-to-end solution, I'd like to break down sort of an architecture for IoT. And fundamentally, we can recognize three primary components. The device, which is the physical object located in the real world. There's often a gateway, which is responsible for collecting data from devices and relaying it. And then a cloud platform, which is increasingly sort of the nervous system of your business or application, where this IoT data can be combined with other non-IoT data to sort of then render useful insight into your applications. Now, if we look at sort of other pieces of this technology stack that data touches throughout, going from sort of bottom to top, you'll recognize a bunch of sort of familiar cloud platform technology pieces in terms of pipeline, storage, analytics, et cetera. And across these things that touch data, we recognize a couple cross-cutting sort of concerns in the areas of device management and security. And so It's often unclear how our cloud pieces necessarily fit into this end-to-end stack. So a lot of what we'll be talking about today is some of the devices and gateway pieces. So with this map or framework, we can break down some of the technical considerations, and we'll kind of use this throughout the talk, starting with devices. So as I said, devices are sort of the thing of the Internet of Things. It's the thing out in the world. But a thing might be as small and simple as a tiny sensor located inside a door hinge, or a thing might be as gigantic as an entire oil rig. And these devices might be compound and mapped in sort of a hierarchy where you might have a ship, and on that ship is a pump. And both of those are related to each other, both are things. And how those are graphed is going to really depend on your specific domain model, your domain specialties. But at the end of the day, a device is a physical thing out in the physical world. And now a device is really just a tiny computer, so it's both familiar and foreign. You can recognize all the familiar components of a computer inside any IoT device. Fundamentally, it's composed of hardware and software, and it is different than the computers of our everyday lives. Fundamentally, the inputs and outputs are going to be very different and a lot more sort of exotic than the familiar mouse and keyboard and monitor that you have on your computer. For sensor inputs, there's a wide variety of sensors available for gases, infrared, et cetera. But an input might be as humble and simple as a button located in just the right place at just the right time for somebody to signal some event has occurred. Now, not all devices are going to have outputs, but outputs can range as well. So you may have something as simple as a buzzer, simply let somebody know that something's happening. An output can be a gigantic hydraulic lift that can lift several tons. So again, these things are what really define IoT devices as different. Now, communications or comms is really technically just another form of input and output. I do call it out separately because the diversity of radios and radio types and communications available for IoT devices makes communication somewhat of a special case for Internet of Things. Now, obviously, on top of this, you run bootloaders, which run and load an operating system potentially, and then all of your libraries and application software then runs on this device. Now, like I said, there's this real diversity and explosion of hardware platforms. It seems like almost every week there's new types of boards coming out, new technology. But really, at the end of the day, as a software developer, you probably think of the device in terms of the information which it provides. How do I model and manage information this device is working with? And we can recognize sort of the four primary kinds of information. The first is metadata. So this is really information about the device. This is things like a device identifier. It might include a firmware version, location date, installation location and date, et cetera. Second is state. This is sort of information about the condition of the device, not necessarily the condition of the environment, but it's a current condition of the device. It might be read-only or read-write. It is going to be something that is along the lines of like the set point for a thermostat or some sample rate for a frequency. And so this is not something you're going to be changing and resetting at very high frequencies. Commands are a type of information which indicate some action to be taken by a device. So this is usually done as some sort of handler or remote procedure call that's running on the device. And these actions are often not idempotent, which means that if you send the same command multiple times, you might not be getting simply the same outcome every time. And you can imagine if you have a command that says, run self-cleaning cycle, and you do that once, and now you're clean. If you keep running it multiple times, it's not necessarily going to change the result the same way it changed it the first time, unlike state. And then finally, telemetry. Now, telemetry is really the eyes and ears of the Internet of Things. It's sort of the source a lot of what we have as the environmental data. And this telemetry can take advantage of that diversity of sensor types I mentioned earlier. Now, if you're going to bother to sort of define a device, pick hardware platforms, and model the information they produce or consume, the odds are you're going to have more than one device out there. And as soon as you have more than one device, you need to consider how you're going to do device management. And device management broadly addresses the tasks required to make these devices functional and useful in your project. And this involves pieces of functionality that run both on the device as well as in the cloud. Now, at Cloud Platform, we're pretty versatile in terms of how we work with you to do device management. We have integrations with Brillo and Weave, which you'll be hearing more about later. That handles device management. We work with a number of device management platform partners who take care of all the edge communications and setup and provisioning. And there are a number of open source and sort of do-it-yourself solutions. But no matter which solution you choose for device management, we can recognize kind of the key functions that are achieved. First is, you need to provision a device onto the network. It needs to be able to connect to the local networking environment where that device sits. You need to register this device in some sort of registry so you can keep track of which devices you have under management. You need to authorize a device. You need to make sure that you're only speaking to devices that are part of your fleet, and you need to make sure that devices can only reach the back-end systems they're supposed to. You need to monitor and perform operational management across a fleet or groups of devices so that you know that collectively, in aggregate, your entire fleet is performing as you expect it to. And finally, you need to be able to ensure that devices are being up to date. Now, this is not only important for making sure the device is gaining new functions over time and new features, but it's critically important for security, that it's always being maintained with the latest security updates. So let's talk about a couple of customer examples. I want to tell you about how Nest has been able to simplify the deployment of connected cameras as part of their ongoing migration from another cloud platform. So today, in the completely regionalized deployment, cameras first must contact a dispatcher in one region before connecting to a home server in another region. And then that data is stored per region. And when it's stored in a single region, it gets copied to other regions for durability and availability. Now, in contrast, the cameras that are now connecting to Google Cloud Platform use our global load balancing service to immediately reach the regional server that they ultimately stay connected to. And the data from that server is stored in services with global storage scope. So they avoid the complexity of needing to synchronize data across regions and get that sort of global availability. Making objects easy and pleasant to use and easy to orchestrate is something Philips Lighting has done successfully with the Hue color-changing light bulb. It's one of the more familiar and sort of widely deployed IoT devices out in the world. Many of you may have one. Now, Philips, with the help of one of our partners, Q42, was able to build and scale the infrastructure to support the Hue application and API on Cloud Platform. This low latency and reliable API is part of the Hue experience, and Philips and Q42 were able to take advantage of some features in Container Engine to allow the back end to this system to be steadily improved and steadily released by taking advantage of a feature such as rolling updates on Container Engine. They're also able to launch new and interesting small experiments very, very quickly on their existing Container Engine cluster, and at almost no cost, no additional cost to run those experiments side by side. And all of that Container Engine infrastructure is then able to connect to our data and analytics and monitoring platforms elsewhere on Cloud Platform. So the light bulb is a great example of a device which by itself cannot reach Cloud Platform. And I'd mentioned gateways in the beginning, and all Hue light bulbs ship with sort of a gateway or hub. And I said this is often a key component in IoT architectures, and I want to explain a little bit more about why that's so. And it comes down to there's a whole class of devices out there that are not able to reach the cloud for one reason or another. And this might be that they do not have any routable connectivity to the internet. For example, Bluetooth is not directly routable to TCP/IP. It might be that they don't have the processing capability to perform the secure HTTPS transport protocol that all of our Cloud Platform APIs require. It also might be that they don't have the power budget in order to support the networking. They may be very low power. And finally, there are perspectives in a setting that require a device to look at multiple devices in that area and do some pre-computing. So any one device isn't going to give you that local aggregate and pre-processing setting. And that's part of what a gateway can do. So we have a demo outside running with Intel. One of our partners in the gateway space is Intel. They make an industrial IoT gateway platform. and we've worked with them on an integration with Cloud PubSub. And the scenario we've worked on is this idea of tracking the environmental conditions and locations of pallet goods. So this starts with an Eddystone Bluetooth beacon. Now, Eddystone is an open source Bluetooth spec from Google, defines a couple data types that are broadcast over Bluetooth, including an ID as well as telemetry frames for things like temperature or humidity. And the gateway collects these from the Bluetooth beacon and then sends the information up to PubSub. On the gateway is also a developer experience, a sort of a developer UI that you can easily connect various sensors directly to the gateway, and then these automatically gain from this integration to Cloud PubSub. The gateway also runs a set of libraries for doing runtime edge processing. And this is useful when you have networking where you want to be somewhat miserly about what you're actually transmitting on the network to the cloud. So if you can do some degree of edge processing, you can really send up the right quantity and kind of condensed version of information. And so this idea of connectivity being a specific challenge in IoT solutions comes up because the location where this information you're interested in is going to be potentially in who knows what kind of environment. And the world is not blanketed with Wi-Fi. Wi-Fi is limited to sort of the places where people are today for the most part. And so one of the ways we're looking at helping extend connectivity to Cloud Platform through partners is with a project we're doing with Particle.io. Now, Particle is one of the more widely used Internet of Things platforms. They've got over 60,000 developers on their platform already. And most recently, they've released the Electron. The Electron is a small, powerful IoT device with built-in cellular connectivity. And so this gives you the ability to have this device connect to the cloud in over 100 countries. And we've partnered with Particle to make it easier than ever to pipe data from any connected Particle device directly into Google Cloud PubSub. Now, anyone who's visited Google may have seen these colorful bikes that we have all around campus called G-bikes. And as Google's campus has grown, the G-bike has become this sort of key way that people get from building to building throughout the day. But the team that operates G-bikes for Google has very little visibility into where these bikes tend to go during the day and how they tend to clump and where they are. So working with Particle, we've sort of attached some of these particle electrons to bikes, and we're able to collect the locations of how they move throughout campus during the day. We stream this through PubSub into BigQuery, and then we can run queries that allow us to plot their locations with heat map APIs in Google Maps. And this is really invaluable for that G-bike team to understand what the usage is and where these bikes are throughout the day. So connectivity involves things like networks, but it also involves things like protocols. Yesterday, we announced alpha support for gRPC for PubSub. And gRPC is an open source binary protocol that we'll be supporting across many of our products. But in IoT, there are other protocols that are very commonly found. And one of those is MQTT. So a partner of ours, Augusto, has been working on building an MQTT solution on Compute Engine. Now, MQTT as a protocol is well suited for IoT. It has a very low footprint, both in terms of network usage, but also is available as libraries for many small microcontroller devices today. And so what Augusto has done is build a custom MQTT broker that is based on RabbitMQ, and it allows us to focus the protocol translation from MQTT to PubSub, and it lets PubSub, as a managed service, handle all of the durability and managed scale of storage of events. So the compute engine, we can focus on using the networking performance and CPU performance, but not necessarily worry about storing all of the events. And this solution allows you to scale this out from pilot to production very cost effectively. Now, what I've been talking about today is how things get solved today. This domain of complexity is all solvable, but it can get definitely better. And at Google, we're working on making it better across the experience. And it's been part of our DNA to work with devices from Android phones to Chromecasts and Chromebooks. So I invite Jeff Chen, product manager from Brillo and Weave, to tell you more about the Brillo and Weave project at Brillo and how we're looking to improve devices.
Thank you, Preston. Good afternoon. So my name is Jeff Chen. I'm one of the product managers on the Google Brillo and Weave team. So I'm a device guy, the hardware guy. And so I wanted to first introduce to you what Brillo and Weave are. This is Google's offering specifically in the IoT space. Well, when we sought out to build out Brillo and Weave, we wanted to address three major objectives. The first one is that we wanted to help device makers build for IoT. So at Google, we have been building connected devices, Android, Chromebooks, Chromecast, and so on. And we realized that these solutions could be benefited from third-party device manufacturers because they struggle with trying to figure out how to make devices cost-effectively or be able to build with security. So we wanted to help device makers prototype their device applications quickly, and then more importantly, port that over to the production hardware without requiring major surgery. And it doesn't end there. With connected devices, it's really important to be in a position where you can actually monitor the devices that are in the field and be able to push out updates to them to resolve any security concerns or to update new features to continue to improve the user experience. Secondly, we wanted to create an open ecosystem. As we observed the growth of these IoT ecosystems, we saw that there were subnets of siloed ecosystems that were causing more and more fragmentation. And while there were some very good reasons for vendors to lock down the connectivity of these devices with proprietary protocols, it keeps us from getting to this truly open Internet of Things. And so the only way that we can get into this Internet of Things is by embracing open and standardized communication protocols, which leads us to the third and final objective that we had, and that is that we can create an ecosystem of devices with open protocols so that we can create a rich ecosystem of apps and services that could be transformative. So think about the web. Think about mobile Android. Now, the intelligence and the smarts of these devices will not come from a single vendor, nor from Google. It comes from you, developers. Developers that want to build applications and services that can communicate across devices from different brands, and that can build rich analytics around these devices to help make these devices better and more useful to the user. So that's why we built Brillo and Weave, because ultimately we see that the magic comes from a distributed world of devices, and we think that the power of this new internet will require the ecosystem to build devices cost-effectively and at scale. These devices have to communicate with each other through open protocols where the smarts are in the device, on clients, or in the cloud. So let me tell you about what Brillo is. Well, Brillo is an operating system that's maintained by Google. It is a version of Android, and it is supported by a variety of silicon vendors. And it has proven scale to reach over 1 billion Android devices, right? So we recognize that deploying a full-blown stack of Android was a little bit overkill for connected devices. So we built a stripped-down version that was targeted specifically for connected devices. So device manufacturers can leverage all of the benefits of the Android hardware ecosystem. So if a chip vendor supports Android, it can essentially support Brillo. Now, the second aspect of Brillo is about security. And Brillo enables devices to be secure because fundamentally we believe that security has to be built into the device for IoT technology. And we believe that not only do you need to have it built in, but you also need a way to be able to fix issues that are in the field as they come up. So we've built a number of security features into Brillo that will address these problems, including verified boot, which means that the device will run code that is trusted from the manufacturer. We also make sure that access to the device and all the data that's produced through these devices is controlled by the user. And that any data that is actually stored on the device or transmitted across the communication pathways are all encrypted and secure. And then lastly with Brillo, it comes with services like analytics and updates. So for example, device manufacturers can get a readout of all the features and the usage of their device population in aggregate and figure out how the users are using their devices. But then also, we provide an infrastructure to push updates so that as security threats come up or you see new features that you want to deploy, that you can have a pathway to be able to push those updates to those devices. Now, for Weave, what is Weave? Well, Weave is our open communications platform. It consists of 3 components: a device library, client API, and a web server, cloud server. If you build Weave into your device, it's easy for third-party application developers to access your Weave devices from their phone or cloud service through Weave Mobile and cloud APIs. We believe in interoperability so much that we built out device schemas for a specific set of device categories so that third-party app developers could use these schemas to build apps to monitor the device state, to control them, and to build analytics and richer experiences across all of these devices. And in addition to offering third-party APIs, Weave also offers seamless integration into Google services, such as the Google Voice assistants. So, with Brillo and Weave devices, this platform enables an ease of use and ease of building devices and creating a standardized device data. And we expect these devices to generate data, and a lot of it. So Google Cloud Platform for IoT data offers a proven end-to-end solution to make sense of large amounts of data and produce meaningful insights. These insights can help manufacturers determine what features to add or remove on their product, help app makers develop novel new experiences and services, and help enterprises manage their fleet of devices for optimal performance and security. So that gives you a little bit of an overview of what Google's doing in the device ecosystem to enable with operating system, Brillo, and a communications platform called Weave. So our team looks forward to all the amazing and awesome things that you guys are going to be doing on the cloud side to take advantage of these smart and connected devices. Thank you. I'll hand it back to Preston.
Thanks, Jeff. So as I said earlier, much of what we've talked about today has been about the technology of the Internet of Things that runs outside of the context of cloud platform. Now, this is important because unless you clearly understand how the on-ramps for IoT data work and how to solve for them, you can't take advantage of all the great big data tools we have on cloud platforms. So it's important to understand how to get the data onto the cloud. But without a doubt, data and analytics is our strong suit on cloud platform. And the key here is that we provide a comprehensive platform for working with IoT data. And what's interesting is as we follow this data through the journey from the edge to the application, it begins perhaps as highly specific data that might be coming from a machine-specific industrial protocol or a healthcare device. But as it moves and is ingested into the platform and processed and normalized and standardized into the structured data that's well suited for our big data tool chain, it begins to lose some of its IoT specificity. Right? Temperatures just become integers, and cycle times on machines become just timestamps. And so as our general purpose big data tool chain processes and sort of munges this IoT data, it then becomes a bit more generic. And as it moves out into the application is where it really regains this domain specificity. Because at the end of the day, the insights and sort of queries that you run against the data are what turn this volume of data into the useful sort of actionable level insights that you need to then present back to processes or users through applications. And this is really why applications sort of called out here separately. And I want to tell you one such application that we've incubated at Google for Work and launched in a multi-store pilot with a retail customer is a solution which provides digital inventory, visibility, and accuracy. Now, this works by putting RFID tags on every item in the store. Readers then on the ceiling can scan the store and basically generate a live inventory feed of what is both in the front of the store and the back of the store. This application then generates this sort of steady stream of the real-time view of the inventory up to cloud platform, where it's processed and analyzed and then made available as an application to store associates. Now, store associates can take this information and it boosts their visibility into the accuracy of their inventory in store upwards of 95% compared to the 60 to 70% typically gained through a standard point-of-sale system. And this allows them to track inventory in the back room to the front of the store to make sure that product is always present where customers need it. The corporate office, this also gives all sorts of visibility about changing and adapting marketing campaigns, adapting store HR hours, et cetera. And once infrastructure such as this is in place, it begins subsequent ideas for other applications that can bring sort of what were once considered far-off future ideas of sort of virtual changing rooms and try-on stores, touchless payment and checkout systems, et cetera. So this is going to bring us back to security now. And security, like device management, is something that needs to touch the entire sort of data handling stack end to end. And you all were in the keynote earlier. Hopefully you heard how much attention we pay to security and cloud platform. It's something that Google takes very seriously, and cloud platform builds into the fabric of all of our products and services. Now for IoT, it's important that we offer both secure APIs and methods for bringing the data onto the platform securely, as well as sort of the security controls and foundations to make sure that you're able to keep that data secure once it's on the cloud. On the device side, you've heard a bit about Brillo and Weave. Device security needs to be built into the fundamental systems and technologies you're choosing. So sandboxing allows the protection of one process from another. Over-the-air updates and verified boots make sure that you're running secure code and always able to push out the latest secure versions. Keeping user data secure on the device and in transit to the cloud is very important for consumer applications as well as sort of commercial applications. And finally, using secure Linux technologies such as mandatory access controls limits the power of any exploit from doing more damage in taking control of the device. But it's not enough for us to just do what we can at Google. To really secure the Internet of Things requires collaboration across a broad ecosystem of partners. So one of the challenges in IoT applications is maintaining this end-to-end integrity and secure ownership of a device. So I want to tell you about this collaboration we're working on with Intel and a technology they're calling Marshall Point. And the idea is that by taking a hardware proof of authentication in this technology Intel calls EPID, which they've already licensed to Atmel and Microchip, that a new owner of a device, a new service of a device, can meet at a virtual rendezvous point the manufacturer or the previous owner of that device, and digitally, sort of through some cryptographic signatures, take new ownership of that device and securely provision it with application or cloud credentials. And so this is an example of what I think it takes to really secure the IoT end-to-end, because if you have any gap in that chain, that becomes sort of an unacceptable point of surface to breach your system overall. So, in conclusion, why do you want to get started building IoT now? Well, it is a fantastic time with the hardware. It's the proliferation and the diversity of sensors and platforms and hardware. It's never been easier to get started with hardware today. Second, Google is bringing its expertise and experience working with both devices and data across the entire spectrum of the IoT problem space. And third, we do so with an utmost focus on security throughout, as you've been hearing. So I encourage you all to think about the analog information that's relevant to you and out there in the world today, and to go start building solutions to capture and process that information on cloud. Thank you very much. We'll let you get cut free to lunch. If anyone has questions, Jeff and I will be down up front. Thank you.